All right, another fun problem here from the book, 5.59. Asks about a hot air balloon. We're going to put air inside that hot air balloon, and the air sample is going to be held at a pressure of 744 torr. Okay, it's a pressure unit. We're then going to take that air and we're going to heat it from 17 degrees Celsius to 60 degrees Celsius. We're to assume the amount and pressure of air is constant, and we want to compute the density of air at each temperature. They also tell us here that the molar mass of air is 28.8 grams per mole. Now, there's a lot of kind of fun things about this problem. All right, one is it's considering the hot air balloons. You know, maybe you had a chance to go over to the Albuquerque area during the balloon festival, and you could see large numbers of these balloons, take flight and carry passengers. And that works because they have a little burner here that's not drawn in my picture, and it heats up this air, and it makes the air less dense at a higher temperature. And as a result, the air inside this balloon is less dense than the air surrounding, and the balloon can rise. You can create some lift that way, okay, and lift even just carriages with passengers in it. So that's kind of a fun thing. We'll get to see that here in this example, okay. Another thing that's a little bit interesting about this problem, it deals with air as our ideal gas, right? And now air, of course, is a mixture. It's about 80% nitrogen, a little less than 80% nitrogen, around 20% oxygen, and then there's a few minor trace gases that make up the remaining 1 to 2%. So since air is a mixture, it's not a pure substance. Air doesn't really have molar mass per se. That you could find from a periodic table, but they give us this 28.8 grams per mole. That's simply the weighted average of the major gases which are present in air. We're going to use that later in the problem, okay? But don't be confused by that. Hopefully you aren't. So we want to compute the density at two different temperatures. So again, I'll draw my line here down the middle to differentiate my two circumstances. Here, 17 degrees Celsius and 60 degrees Celsius. Okay, so I'm going to do a calculation for both of these. Now, you've got to think a little bit about how in the world are we going to arrive at the information that we want. Well, let's think about this ideal gasol that we've been working with, PV-nRT. We want to compute a density. A density is really a mass or maybe a number of moles per volume. Okay, now if I look at the key terms in my PV-nRT relationship that relate to those, it's these two. So I could, in fact, if I want to, rearrange this equation such that I have N divided by V, which of course is number of moles of the gas divided by the volume of the gas. If you start thinking about it, that tells me something about the mass per unit volume, which is kind of akin to a density. Now, what did I need to do to make this? Well, I had to divide both sides by the V first off, okay? Which kind of leaves P out by itself over here on the left side. But another thing I had to do was divide both sides by RT to clear it from the right. Okay, so what I've got, if I rearrange my variables, is N over V, my proxy of density, is equal to P divided by RT. All right, so I simply rearranged the gas law to give me something in the form that tells me about density. Now I can run with this. N over V is equal to P divided by RT. I'm going to use an R value of 0.082 as I characteristically do, but I remember that if I do that, I need to use liters and pressure units. Liters and pressure and atmospheres for pressure units, okay? Now in the problem, I was told P is equal to 744 torr. Now that is not in atmospheres, so I need to convert. So one of the first things I need to do is divide by 760, the reasoning being that 1 atmosphere is equivalent to 760 torr. If I do that, I find that the pressure in this instance is 0.9789 atm. And I'm going to plug that in the numerator, 0.9789 atm. Going to divide by my r. I just need to plug in a t. Now you might think, oh, I'll just plug in 17, right? But that would be, of course, completely wrong. Because whenever you use these gas laws, you must use Kelvin temperatures. So I need to convert to Kelvin, okay? The way I need to do that is I need to take my 17 degrees Celsius. And you have Celsius temperature, you just add 273. That's your Kelvin temperature. So I'm taking 273, adding 17, that yields 290. And if I complete this calculation out, my N over V is 0.041168. That's going to have units of moles per liter. That's the number of moles per liter of air at that temperature. Now likewise, I come over to the right side, repeat the same calculation with a higher temperature. I was told in the problem that the pressure is to be assumed to remain constant. In both cases, the pressure is the same, 0.9789 atm. So that hasn't changed. Okay. My R, my gas constant, is always 0.082 if I'm using units of liters and atmospheres. But now my temperature is 60 Celsius. Okay. But again, if I do 60 plus 273, I can go to Kelvin. That gets me 333. Now I can do the math on this to get my N over V term. And if I do that, I get 0.03585 mole per liter of air. Okay, so I've got a density at the low temperature. I've got a density at the high temperature. Now these are not necessarily in mass per volume. Instead, it's moles per liter. It's kind of a consistent unit with molarity almost. We learned about molarity earlier. And it's kind of a measure of density for a gas. I mean, you could think of it that way. How many moles per volume? Of course, moles are related to a mass. But to finish this problem off, it really might be nice if we could convert these into a mass-based unit. Like how many grams per liter do we have? And we can do this pretty straightforward, okay? The reason why is because we were told here in the problem what the molar mass of air is, okay? So think about this for a second. If I have 0.03585 moles per liter of my air, and the molar mass is 28.8 grams per mole, my mole units can cancel out, and I'll be left with units of grams per liter. Grams per liter is clearly a density unit. So if I do the multiplication, I get 1.0325 grams per liter, a little over 1 gram per liter for my density at the higher temperature. And I could do the same exact calculation for the lower temperature, 0.041168 mole per liter. Multiply by 28.8 grams per mole. Mole units cancel. And in this case, I get 1.1856 grams per liter. So two different temperatures, two different densities. At 17 degrees, the air has a density of 1.18 grams per liter. At the higher temperature, the density of air is much, much, much less. For every liter of air, the density is about 0.15 grams less. So now I think you can see how the hot air balloons function, right? If we're able to successfully heat up the air sample very hot, or relatively hot, right? That makes this air a lot less dense than the surrounding air. So it becomes a lot like, one of those styrofoam floaties floating on your swimming pool. It's a lot less dense than the water it displaces. So the air inside this balloon is a lot less dense than the air out here, and that balloon will rise as a result from buoyancy. This is a fun little problem.